Between 1951 and 2003, only 17 hurricanes have struck the coastal regions of New England and the eastern Canadian provinces, less than 5% of the total hurricanes in that period. 0 major hurricanes, category 3 or greater, have made landfall in this region, and the majority to do so were weaker category 1s. But sometimes it's not the strength, but rather the infrequency that makes a storm incredibly dangerous. Infrequent severe weather events receive less preparation, emergency management resources, and mitigation infrastructures in areas more commonly affected by these disasters. And such is the case for Hurricane Juan. Striking Nova Scotia on September 29, 2003, it became the strongest hurricane in history to make landfall on the Canadian coast, battering Halifax with wind gusts greater than 130 miles an hour, creating 60-foot waves near Halifax Harbor, damaging a third of the city's buildings. Just 5 months later, in the midst of a national recovery effort, a second hurricane-strength cyclone slammed into Halifax, dumping over 3 feet of snow on the city in just 24 hours, a record that still stands today. Nicknamed White Juan, many residents questioned if the storm was related to the record-setting hurricane that occurred just a few months prior. Today, we'll dive into the difference between Atlantic tropical and extratropical cyclones, analyze the meteorology behind these two powerful storms, and comb through the incredible damage left behind in southern Nova Scotia. Now, between June and December, an average of 14 tropical disturbances form and meander towards the United States, with about 7 strengthening into hurricanes. 3 of those become major hurricanes, category 3 or greater, and 2 make landfall on the United States. The worst hurricanes strike the Gulf and southeastern states, like Georgia and the Carolinas, but nowhere on the Atlantic seaboard is safe. Strong hurricanes that travel northward can become extratropical, developing fronts that bash into the coast, bringing colder air, storm surges, high winds, heavy rain, and tornadoes. Hurricane Sandy in 2012 is an excellent example of the transition to an extratropical cyclone. But exactly how far north can one of these hurricanes travel in the Atlantic while staying barotropic? Well, first let's define barotropic and baroclinic. Barotropic refers to a weather system where the temperature is uniform across a constant pressure surface. Now, when we say constant pressure surface, we mean finding everywhere in the atmosphere where the pressure is the same, taking that two-dimensional plane and mapping other variables like geopotential height, temperature, and wind speed across that plane. If we map temperature across a given pressure in a barotropic environment, we would see a constant temperature in the X and Y directions. But if we did the same procedure in a baroclinic environment, we would see a temperature gradient or change in the same XY plane. This change in temperature is a frontal system, and thus baroclinic weather systems have fronts. All mid-latitude cyclones that sweep across the interior US have fronts, and all hurricanes that form in the Atlantic do not. However, both systems are just areas of low pressure, and so it's possible that a barotropic hurricane can transition into a baroclinic cyclone when it meets colder air. First, let's take a look at some of the factors that influence this transition between cyclones. As you move away from the equator, you encounter more wind shear, or change in wind direction and speed with height. This is because you get closer to the jet stream, the fast-moving band of wind that encircles the northern and southern hemispheres. Hurricanes don't do well with wind shear. If the wind is too fast high in the atmosphere, it will literally blow the tops off of the individual cells that form the spiral bands of rain, tearing the hurricane apart. Hurricanes also feed off of warm water. Near the equator, the water temperature is nearly uniform, but as you go north, the temperature starts to cool. At some point in a northward moving hurricane's life, it will reach a place where on the northern side, the wind shear is greater and the temperature is colder. This is when the magic starts, and to observe it, we need to look at something called thermal symmetry. By comparing the thickness of the atmosphere between the 900 and 600 millibar levels on the northern and southern side of the hurricane, we can pinpoint the exact moment a thermodynamic response occurs. The threshold being when the difference in the northern and southern thermal thickness exceeds 10 meters. At the same time, the warm core begins to collapse. Warm core lows have a very recognizable structure in that the column of low pressure is nearly vertical, with an area of high pressure sitting aloft. As the warm core weakens and transitions into a cold core, this column of air at the center becomes vertically skewed to the northwest. Now with hurricanes, the strongest winds are located a very short radius from the center in the eye wall. But as extratropical transitioning occurs and the hurricane becomes asymmetrical, the radius of maximum wind moves away from the center, expanding the wind field. Features called conveyor belts begin to develop, which transport both warm and cold air around the low center. The warm conveyor belt pumps warm, moist air located in the southeastern quadrant northward, while the cold conveyor belt pumps cold, dry air to the north of the low westward. As extratropical transition occurs, these two conveyor belts increase in speed. A thin cirrus shield will often stretch far northeast of the low center during this process. Precipitation on the western side of the cyclone will decrease as drier air intrudes, but stronger convection will develop to the east as warm and cold fronts begin to take shape. Cold, dry air dives thousands of feet down from the upper troposphere, wrapping around that western side. This is a process known as dry air intrusion. When an area of low pressure forms beneath or approaches a long wave trough, the area of positive vorticity advection, or spin, in the atmosphere caused by that curvature of the jet stream aids in the transport of cold, dry air tens of thousands of feet high in the atmosphere downwards, which wraps around the low and blasts eastwards with the associated cold front. This causes a very recognizable clear slot on the southwestern side of most mid-latitude cyclones, and during extratropical transition, this slot becomes more pronounced. Now, this extratropical transition can occur both over water and over land. In October of 2012, Hurricane Sandy, a massive Category 3 storm off the mid-Atlantic coast, had shown the classic characteristics of extratropical transition a few hours before landfall on the Jersey coast. Colder waters and the influence of the jet stream around a large ridge in northeastern Canada were responsible for the erratic motion and loss of tropical characteristics. In 2008, Hurricane Ike, a Category 4 hurricane, made landfall in Galveston, Texas, interacted with a strong cold front to the northeast, became a strong extratropical low, and caused hurricane-force winds across the entire Ohio Valley. 2025 is here, and whether your passion is storm chasing, going to concerts, or traveling, you should prioritize it by cutting back unnecessary spending in other places. However, this can be difficult. Media subscriptions like Spotify and Hulu are important to my lifestyle. But thanks to today's partner Mint Mobile, I can keep my favorite subscriptions and still save money with their premium wireless plans starting at just $15 a month. They provide high-speed data and unlimited talk and text on the nation's largest 5G network for just a fraction of the price of the other major cellular network providers. I don't have to sacrifice anything either. I can keep my current phone, contacts, and phone number. But how is the coverage? Reliable cell coverage is a must for a meteorologist on the go, so let's drive to rural Ohio, far from the interstate, and give it a test. It's great. I can stream 4K YouTube videos in the middle of nowhere, receive texts and calls, navigate to the nearest gas station that has pizza, and check the weather. It's cold. Big Wireless wants you to think it's difficult to switch providers, but switching to Mint Mobile is super easy thanks to digital eSIM cards. You can sign up and activate your device immediately right on your phone from the comfort of your own home. And if your phone doesn't have an eSIM, no worries. Mint Mobile will ship you a new SIM card for free. If you want to save money on your phone bill without the sacrifice, go to trymintmobile.com/weatherbox, link in the description below, to get premium wireless for just $15 a month when you purchase a 3-month plan. Thank you, Mint Mobile, for partnering with Weatherbox and for saving you money in 2025. Now you have an understanding of why extratropical transition occurs. So the question becomes, is there such a thing as a tropical transition? Can an extratropical cyclone, which has fronts and feeds off of temperature differences, transition into a vertically stacked tropical cyclone that feeds off of uniformly warm water? Well, technically yes, but rather than a fully formed, full-strength extratropical cyclone transitioning into a tropical one, weak baroclinic environments over warm water can often initiate the formation of a weak extratropical cyclone, which can then transition into a tropical depression within about 24 to 48 hours. A great example of this is Hurricane Diana in 1984. A cold core baroclinic cyclone moved off the coast of Florida with an associated warm and cold front, but the frontal system stalled out. You can then watch the stationary cyclone lose its extratropical characteristics like the clear slot and band of heavy convection stretching to the northwest, and develop an eye within 24 hours. The crucial piece is that while the baroclinic environment caused convection in the first place, which led to the tropical transition, in order for the hurricane to survive and strengthen, the wind shear and the temperature gradient had to weaken significantly. And it did. In the coming days, Hurricane Diana meandered northward and hit the Carolina coast as a Category 2 storm. Tropical transition on this magnitude, however, is much rarer of an occurrence than extratropical transition. There are some rare cases where hurricanes move incredibly far north over warm water while maintaining their tropical identity. In September of 2021, Hurricane Larry tracked northwestward off the coast of Africa, intensified into a Category 3, turned north and hit Newfoundland as a weak Category 1. 60,000 residents were without power and many buildings saw light to moderate damage from high winds and fallen trees. In September of 2010, Hurricane Igor took a nearly identical path, impacting the eastern side of Newfoundland, dropping nearly 10 inches of rainfall in St. Lawrence. But the strongest tropical cyclone to hit the Canadian coast was Hurricane Juan in 2003, a Category 2 storm that battered Halifax and central Nova Scotia. The formation of Juan started off the Liberian coast of Africa on September 11th when an easterly wave, or a trough of low pressure within the trade winds, moved westward into the Atlantic. Over the next week, the wave intensified, and on September 21st, it entered a marginally baroclinic environment. Situated in the center of the North Atlantic was a cold core frontal system, and extending to the southwest was this closed circulation where weak convection was taking place. As the easterly tropical wave crossed this area, localized convection intensified. The far eastern extent of a long wave trough that had crossed North America was now approaching this area, and upon crossing the area of convection, the storm rapidly intensified. At first, it exhibited more extratropical characteristics than tropical, but with the long wave trough retreating, the environment got progressively more barotropic, and the NHC labeled this disturbance as Tropical Storm Juan in the evening hours of September 24th. The decision was a difficult one, as suggested by the forecast discussion written by Dr. Lixianavala, stating, "There are no clear-cut signs, and we could have gone tropical or subtropical at this time." At this point, Juan had a very interesting synoptic environment ahead. To the west, an unusually deep long wave trough existed over the central United States. High temperatures were squarely in the 60s in the upper Midwest the third week of September. To the east, an amplified ridge of high pressure was building over the Atlantic, providing an anomalously warm, high-latitude synoptic environment for Juan to utilize. 48 hours later, the NHC classified Juan as a Category 1 hurricane. Although Juan was now largely a tropical system, if you looked at the center of the surface low, it is still directly below an area of positive vorticity advection, which is a feature you would see with baroclinic cyclones. The environment was still slightly baroclinic, and the model suggested the storm would weaken and go extratropical before making landfall on eastern Canada. But instead, aided by the strong southerly flow due to the North American trough and Atlantic ridge, Juan strengthened and moved swiftly northward toward Nova Scotia. Now, between 1948 and 2002, there were only 8 northward moving hurricanes that made landfall poleward of 40 degrees north latitude. The synoptic environment for each of these 8 hurricanes involved height anomalies at 500 millibars from Newfoundland to Greenland, indicating a significant ridge over the northern Atlantic. Additionally, an amplified trough over the eastern US was present, further increasing southerly flow on that eastern side. By noon Atlantic on September 27th, the hurricane had reached its peak intensity with a central pressure of about 970 millibars. It did so at about 34 degrees north latitude. Now, the National Hurricane Center and Canadian Hurricane Center were hard at work forecasting Juan's landfall, and the consensus was it would continue on that northerly path and hit Nova Scotia. But the intensity of the storm, or whether it would undergo extratropical transition, was was much more difficult to forecast. At the very least, the storm was expected to weaken considerably as it entered the colder baroclinic environment in the far northern Atlantic. Two global models, the GFS and the GEMG, failed miserably at producing any useful guidance to forecasting hurricane landfall. However, NOGAPS and UKMet were fairly accurate in their hurricane tracks as they used tropical cyclone initialization techniques that were far more advanced than the GFS and the GEMG. Interestingly enough, the Canadian Hurricane Center did not issue hurricane warnings, but rather issued warnings for the hazards that hurricanes produce. In the early morning hours of September 27th, hurricane-force wind warnings were issued for the marine areas to the south of Nova Scotia. While Juan was starting to weaken due to increased wind speed and decreasing surface temperatures, it was actually accelerating northward, so while the winds in the hurricane decreased by 10 miles an hour, it was counteracted by the forward speed of the entire system increasing by 10 miles an hour. At 3 p.m. Atlantic Daylight Time, the Canadian Hurricane Center issued heavy rainfall warnings for rain in excess of 80 millimeters, or about 3 inches, as well as wind warnings for sustained winds of 90 kilometers an hour with gusts to 150, which is 55 and 90 miles an hour. One concerning factor is the coincidence with the high tide in the Bedford Basin. If Juan made landfall in the early morning hours of Monday the 29th, the storm surge would be significantly higher than forecast. A storm surge of over 6 feet was probable for coastal areas just to the east of Halifax, which would also likely flood the lower-lying downtown streets. Thankfully, with it being a Sunday afternoon, most businesses in the area closed early, and residents would be home for the night. There were a number of Halifax residents who were quite excited at the prospect of a hurricane hitting their town, and there were accounts of young adults gathering near the waterfront late Sunday evening to experience the once-in-a-lifetime event. But just after midnight, the storm made landfall with an intensity that shocked everyone. At McNabb's Island, just off the coast of Halifax, sustained 2-minute wind speed measurements read 100 miles an hour, making Juan a clear Category 2. The convergence of winds rushing into Bedford Basin likely caused the local increase in wind speed. Thousands of thin, tall spruce trees were flattened on the island, as well as in Point Pleasant Park, as shown by these before and after shots. The surge pushed sections of the boardwalk on the Halifax waterfront out to sea. Small boats and yachts were pushed by the wind and waves into jumbled piles. One of the ships affected was Lorinda, a schooner built by Larry Mahan to look like the HMS Sultana. It now sat on the Bedford Basin floor. As the wind and rain blew through downtown Halifax, powered lines began to snap, telephone poles toppled, roofs began lifting off of buildings, and floodwaters rose above sidewalks. The sound of a freight train engulfed Halifax for the next few hours. Semi-trucks traveling along Highway 102 were at great risks of flipping due to hurricane-strength crosswinds. 10 train cars were derailed and nearly a mile of track was badly damaged. Roof debris littered downtown while deciduous tree limbs littered suburban lawns and streets. Residents mentioned the smell of tree sap when leaving their homes that Monday morning due to the sheer number of downed spruce trees. The seaside community of Prospect had lost every one of its wharfs. Countless fishermen who utilized old sheds along the waterfront woke up to piles of driftwood in their place. School was canceled a week after Juan hit as the cleanup commenced. The damage to the tree canopy was unprecedented. The only comparable event was the Halifax explosion of 1917, where a French cargo ship containing high explosives caught fire and obliterated every structure within a half-mile radius. The biggest loss here was the spruce trees. 20 years later, these affected areas saw many more deciduous trees take hold, which are actually more resilient to severe winds. A few hours after landfall, Juan underwent extratropical transition and weakened considerably, exiting Canada as a strong mid-latitude cyclone. 300,000 Nova Scotia residents were left without power for at least 3 days. A third of the buildings in Halifax and 4 out of every 5 homes saw tree damage on the property. Within the following 3 weeks, Halifax saw 2 extratropical cyclones bring gale-force winds causing even more damage to the area. Juan was a big wake-up call for maritime Canada. Hurricanes making their way that far north while maintaining tropical structure were not common in the few decades prior to Juan, but since then have happened once every few years. Now, 4 months later, in mid-February, a strong cold front had made its way across the eastern United States. A surface low had formed off the Carolina coast and moved northward rapidly. Being extratropical in nature, it was fueled by the temperature contrast between the warmer water and cold land, picking up moisture from the Gulf Stream, which condensed and fell as heavy snow. With a central pressure near 970 millibars, the cyclone slammed into central Nova Scotia on February 18th with sustained hurricane-force winds. For an area with a climate not conducive to regular heavy snowfall, 3 feet of snow fell in just 24 hours, stopping Halifax for several days. Residents were notified days in advance that a nor'easter was likely to form, and it would bring at least a few feet of snow to central Nova Scotia. The central pressure of this particular cyclone dropped by 37 millibars in just 24 hours. That is an explosive rate of intensification, and if you recall, the definition of a bomb cyclone is one that deepens by at least 24 millibars in 24 hours. The storm set 24-hour snowfall rate records at the time, and due to its occurrence in proximity to Hurricane Juan, the cyclone became known as White Juan, despite sharing hardly any meteorological characteristics. For a place that doesn't see the lion's share of severe weather events, receiving back-to-back record-breaking cyclones of such opposing nature in such a short period of time is something that the residents of Halifax will never forget. I hope you guys enjoyed this look into a pretty unique hurricane that I think is often overlooked. If you want to send me any weather-related stuff, my mailing address is right up here. Otherwise, I hope you guys have a fantastic holiday season, and I'll be talking to you soon.